It's Math and Beats, and it's geometric series. Time to talk about some series, and these ones are geometric, whatever that means. Let's take a look at this. Okay, first of all, let's just define it. What's a geometric series? Well, has the form, either a series that looks like this, summation, k goes from 1 to infinity of some number a times r to the k minus 1, or if you want to start your index at 0, which is often very convenient, then k is 0 to infinity of a times r to the k. First of all, we assume that these values a and r here, they're both real numbers and a is non-zero. We especially don't want a to be 0, because if it was 0, then every term in this series would be 0. Just add up 0 forever. Not that interesting. R being some real number, though, and our job is to investigate for various values of r what's going to happen with this series. That r value, speaking of, is called the ratio of the series, right there. It has a special property for the series, as we're going to see. So we call it the ratio. Kind of tells us what's going on. And notice, just write it out, right? What is this series? So let's just take the form when the index starts at 0 and then go to infinity of ar to the k. Then what is it? K is 0, you get a. K is 1, you get ar. K is 2, you get ar squared, and so on and so on. Add up all that stuff. K is n, you get ar to the n. Add up forever. That's the series. That's what we're interested in. Now, of course, every series, by definition, is the sum of all these terms, but it's also the same as the limit of the sequence of partial sums in the series, as we discussed before. So what are these sequence of partial sums here? Well, notice S1 is just the first term, right? A. S2, add up the first two terms. A plus AR. S3, add up the first three terms. A plus AR squared. How about the nth partial sum? What if you added up the first n terms? Well, notice the relationship between the highest degree you see on the term in the partial sum is always one less than the index on the partial sum. So add up all the terms starting at the first one, a plus AR squared. Keep adding them up, and actually the nth term is right there. That's the nth term. So hence, what is that? It's the same as adding up all the terms from 0 as an index to n minus 1. That's the nth partial sum. If we could take the limit of that as n goes to infinity, we could figure out what the value of the series is. That's the goal. So, notice, you might be wondering why we're doing this for a second, but just check it. If I multiply S of n, the nth partial sum, by r, then I'm going to get all terms multiplied by r. So the first term is going to become AR, second term AR squared, third term AR cubed, and so on and so on. And nice about this is now it will end at n. And so that's of some use, because if you then take the partial sum, the nth partial sum, right here, and add it up with the negation of r times S of n, just a fancy way of saying take S of n and subtract r times S of n. Of course, r times S of n we just saw right here. So that's your r times S of n. And why are we doing this? It's supposed to help us. We'll see. Notice a bunch of stuff cancels. AR minus AR. AR squared minus AR squared. Somewhere in there, there's an AR cubed. Next one, minus AR cubed. All the way down, AR to the n minus 1 minus AR to the n minus 1. What's left? Only A and AR to the n. So, S of n minus R S of n is A minus AR to the n. And then notice that if you factor out an S to the n from that up there, factor it out, s to the n, common factor. You're left with s of n times 1 minus r. And then on the right-hand side, of course, common factor of a. Factor out that a, get a 1 minus r to the n. So we could solve that equation for s of n, and actually, that s of n that we showed before is really just equivalent to this value a times 1 minus r to the n divided by 1 minus r. It's the same thing. So we're still interested in taking the limit as n goes to infinity of this, because that would be the value of the series. And that's what we're saying right down here. What's the value of this series, this geometric series that we're interested in? It's the same as taking the limit as n goes to infinity of the nth partial sum, s of n, which is the same as the summation from k is 0 to n minus 1 of ar to the k. And that's the same as limit as n goes to infinity of the thing we just found, a times 1 minus r to the n over 1 minus r. So that's what we're going to do. We're going to take that limit, see what's up. So in order to figure out what that limit is, let's just refresh a different limit. And that is the limit of the geometric sequence, r to the n here. So remember from previous video, if r has a magnitude less than 1, then that sequence is going to converge to 0. Think exponential decay. If, however, r equals 1, then that limit is 1, because it's just 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. And then otherwise, it doesn't exist for reasons that we previously stated. So go watch the other video if you want a further explanation of that. So we got to refresh that. Why? Because in that limit up there, n is the thing that's changing, right? N's going to infinity. And the only piece of that puzzle that has an n associated with it is r to the n. So we're going to look at these different cases here. So it gives us the cases. Okay, first of all, if r has a magnitude which is less than 1, then let me rewrite it down here so we see it. Limit as n goes to infinity of that nth partial sum is the same as the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Okay, now we just look at that limit. We already know it from before. If magnitude of r is less than 1, then r to the n goes to 0. Of course, this expression inside the limit is the same as a minus ar to the n over 1 minus r. So really there's two terms there, and that's the same as saying a over 1 minus r minus ar to the n over 1 minus r. So if r has a magnitude less than 1, that second term is gone. You're left with a over 1 minus r. That tells us the series converges if the magnitude of r is less than 1. And more specifically, it converges to the specific value, a over 1 minus r. That's great. But what about the other cases? What if the magnitude of r is bigger than 1? Then, of course, the limit as n goes to infinity of s of n does not exist, and hence the series diverges. Again, because that r to the n is appearing in our limit for the sequence of partial sums. And so we know if the magnitude of r is bigger than 1, then the terms in r to the n keep growing and growing and growing in magnitude. We add up bigger and bigger and bigger values in magnitude. Whether they're alternating or not, it's still going to diverge to some number that's not a unique real number. And then finally, there's the third case. What about the magnitude of r equal to 1? Okay, so there's really two cases in this last case. If the magnitude of r is 1, okay, then what do we get? Well, either you have r is 1 or r is negative 1. In the first case, if r is 1, then, because remember, what are we adding up? A, r to the k's inside the series. So if r is 1, then r to the k is always just 1. So you get the series k is 0 to infinity of a, which is a plus a plus a plus a plus a plus a, and so on forever. That's just going to become infinite in magnitude depending on the sign of a. So that diverges. So they're going to converge in that situation. And the last situation is if r is negative 1, then again, remembering, we got the series AR to the K. Common factor is A. I'm going to take that out in front because I can. And then I'm left with negative 1 to the K because R is negative 1. So how's that work? What do we get? First term's A. Second term, also A, but it's negative. Then you add a positive A. Then you subtract an A, plus A, minus A, right? We keep making K as 1, 2, 3, 4, and so on. It's just going to be 1, negative 1, 1, negative 1, so on, times that A. So if I add up the first two terms, it's 0, but then I'm back to A. Then I add up these two terms, 0. Then it's back to A, and so on. So it never actually converges to a real number that's unique. It just, the sum just keeps going back and forth between A and 0. And for that reason, we say the series diverges there. Hence the conclusion. The conclusion is you got real numbers A and R. A is non-zero. Then what we have discussed and shown is that series, the geometric series from K is 0 to infinity of AR to the K, converges if the magnitude of R is less than 1. And moreover, it converges to something specific. A over 1 minus R. Otherwise, it diverges. So basically, first case is what we're really interested in the sense that care about when it converges. And if it doesn't do that first case, when the magnitude of R is less than 1, it's going to diverge. So we did it. We showed it. What's geometric series? We defined it. And then we came up with when that series actually converges or diverges. So that's it for what I want to do in this video. Show you how all that works, how we came to the conclusion, and then make a video after this, next one, in which we look at a couple of different examples. We explore whether a series converges or diverges, and if it does converge, what to? Specifically for geometric, of course, for the time being. So whatever, that's it. I hope that helped give you perspective about geometric series, and I hope you watch the next one too, because it's all Madden beats. All right, then.